This is part 4 in a series of videos in which I'm attempting to repair this Mimi 802 vintage computer, and in particular I'm trying to repair it and also get it to boot from floppy disk. A friend sent me some images of floppy disks and the files for them that we believe should boot a Mimi 802. However, I had been trying to use them initially to boot a Mimi 803 without much success, and we thought that if we tried the disks on this 802 then at least it would give us some indication as to whether we had the right formatting for the disks and whether they were actually boot disks. There's always some ambiguity over old software, as I'm sure you're aware, that sometimes they will work and other times they won't. But they wouldn't boot on the 803, so a friend lent me this 802. Now it needed a bit of work to get it up to the point where it would actually boot up to the monitor program, and in the last video I showed that I'd got as far as doing that. Needed to do some work on the power supply, a couple of ICs needed changing on the main board, in particular the buffer that fans the clock out to all the devices, although it was working, was very weak and it wasn't properly clocking all the devices. That's now working. I've corrected all that. I've also replaced the socket that the floppy drive controller sits in. It was a very flaky socket and it was sometimes working, other times it was doing strange things. I was hoping that was the fault, but it turned out not to be the case. So although the machine is running, it still won't boot from floppy disk. So the next step was to try and figure out what was going on. And I won't go back over this because I showed this in the videos for the 803, but the first step I took was to really go over the same ground I had with the 803, and that is to monitor certain parts of the system. Now in particular, with the way this is arranged, it uses an FD1797 floppy drive controller chip, but it uses that in conjunction with this device, as does the Mimi 803. So these two devices are used as a chipset along with a clock generator chip, and this is an external data slicer for the floppy drive controller, and then this is the floppy drive controller itself, and together they should give all the logic and control and decoding for reading, writing and formatting floppy disks. But of course, as I say, they're not working. So one of the things I monitor when I'm trying to look at this is the output pin of the floppy drive controller chip. So in particular we have the interrupt output and the DRQ. The DRQ is a data ready line, and that changes state whenever the floppy drive subsystem successfully reads a byte from the floppy drive. But that was never changing state, so the system was never successfully decoding a byte from the floppy drive, and that was despite the fact that we had good raw data going into the floppy drive controller chip, and also the data stream could be locked onto by the floppy drive data slicer, which is this device. And the way that this works is because the data stream from the floppy drive is variable in speed, there's a closed loop voltage controlled oscillator that's used to lock the frequency of the data slicer clock so it matches the data that's being read from the floppy drive. And that was all working. It was giving the correct values, the correct frequencies, but it was never reading a data byte, so we were never getting this data ready output. Now this pin is not actually used directly by the system, so it's not actually connected to anything. But even so, it's the state of this pin is a duplicate of an internal register within the controller chip, and that's what the Mimi uses. It just reads it as a status register from within the chip, but we can still monitor this pin because in whatever mode you put it in, this pin should change state whenever a data byte is successfully read. Now, because the data on a floppy disk is not stored as a continuous stream of data, it can be quite difficult figuring out exactly how to read these if you don't have the proper formatting information. So the way the data is arranged on here is you have circular tracks and then if it's a double-sided disc you might have tracks top and bottom, which is the cylinder, and then each of those tracks is broken up into segments, which are called sectors. And in order for the system reading the floppy disk to make sense of this, there are header sections that are used to tell the controller that's driving the floppy drive exactly what the parameters are it needs to use to reach the actual data. And if you don't know exactly what those settings are, then you'll struggle to read the floppy drive. And that's the problem that we're having, that we're fairly sure these are the correct disks that these are taken from, but these are not the originals, so we don't know exactly if we've got the formatting correct from the original disks. But these are so rare that we don't really want to risk the original disks straight away by putting these into the machine until we're fairly certain, at least, that we've got the machine fairly well under control. So that's what I'm doing here. I'm trying to make this machine either boot or at least get it up to the point where we can say there's no danger it's going to damage an original disk if we try to use that to boot. But even so, we still need to figure out what's going on, because of course we'd like to make some disks that we can boot this machine from. So the next thing I did was to break out the floppy drive emulator, figure out exactly how to make this match the exact results I was getting from the hardware floppy drives, and once I'd done that I could experiment and try and figure out what was going on. And what I found, it's a fairly easy fault to fix once I found out what was going on, but as I say, the data goes into this device and also into the floppy drive controller, and internally it goes through several levels of checking to make sure that the ID bytes in the header match these settings within the registers in the floppy drive controller. And then there's a checksum and various other things it looks at, and if any of those are wrong, it just doesn't output any data. But what was wrong with this? If we look at a sample application circuit, so this is a typical application circuit that's shown in the manual. This is not the actual circuit that's on this board, but it gives you an idea as to how it's laid out. So what we have is the floppy drive controller chip, we then have the data slicer controller chip, and then we have a voltage controlled oscillator. The raw data goes into both the floppy drive controller and the data slicer. It goes into the data slicer so that the clock can be extracted from the incoming data stream, and that way this device can accurately choreograph the way that the data is sliced and turned back into valid data bytes. And for this to work, because the clock that's essentially embedded within this data is variable and also slightly unknown, because it's a mechanical drive, it might run at slightly the wrong speed. You have this closed loop control system centered around a voltage controlled oscillator device, and what this does is it generates a very well defined clock from the incoming data, and that's used to control the data slicing, which in turn is used to control the floppy drive controller. This choreographs all the timing, this generates the correct time time clock, and then they all work together to accurately slice the data that's coming in and present decoded data bytes to the host CPU. The problem that I had, it wasn't ever asserting the DRQ line, so there's something failing in the checking, even though we could see data was coming in. And it turns out that the value of this capacitor was wrong, and so what was happening is this was hunting up and down slightly too much for it to properly lock into the data. It was locking into the right frequency, but not quickly enough, and it was lagging slightly behind what the data was doing. And I think the capacitor was just leaky, so it wasn't giving the correct response for this. This is not the right value, this is for a different setup, but I then changed the capacitor. You probably can't actually see it, it's sitting down behind all this mess. I changed that for the correct value, and so the data slicer then started working, and we started getting a DRQ output, which is where I am at the moment. I have gone further than this. I'll explain the next steps that I took. but we are now getting actual data slicing. As I say, the system still doesn't boot, but I'll show you how far I've got and what the next steps were that I took. So I'll just pop the floppy disk back into the drive. I'll power up the machine, and if you watch the scope you'll see that as it tries to boot up we're getting activity on the scope, and that channel is connected to the DRQ line on the data slicer. So in other words, every time that signal is asserted on the scope, then a new data byte has been decoded and is ready on the floppy drive controller chip. So I'll reboot the MIMI. You'll see the scope again showing activity as it decodes data, and you can see it's fairly brief. It's only decoding one sector, and what we'll do now is look at the logic analyzer, and I'll show you what I did once I'd got to this point. So what I started by doing was reverse assembling the code from the MIMI ROM. This is the same process I did with the 803, and I extracted from this the part that deals with the floppy disk controller. And this is almost identical code. The only thing that's really different is it's in a slightly different address, but the code itself is almost identical, so I won't go back through how it all works. Suffice to say, it goes through, configures the floppy drive controller chip, and then as it goes through it loads the head, it selects track 0, sector 0, and then it goes through and there's a few checks it makes on the internal flags within the floppy drive controller chip. If I go to the next page, okay, so looking at the next page, the instruction we're particularly interested in is the one down here, and of course I've annotated this, so I've added all these comments to say what each particular section does. And the instruction we're interested in, and this is a Z80, is this one, the INI. It's quite a powerful instruction. It uses a couple of the registers within the Z80, one to point to the port from which to read data, that's the C register, and one to point to memory where the data being read from the port will be saved, and that's the HL register. And I showed those being loaded previously, but just in brief, the data is going to be read from port 23 and saved beginning at address E000, and the instruction will then increment the memory pointer so that the next byte read will point to the next memory location. So it's quite a good, nice instruction for this sort of thing, and all we should need to do is iterate around a small loop, reading data from the data port on the floppy drive controller and saving that to the memory location currently pointed to by the HL register. But if you recall, we were never getting to this instruction, but now we should get to this instruction, and we need to trigger on F0 E0. Again, if you're wondering why we're triggering on F0 E0, if you go back and look at the previous videos I've done on this, it's to prevent us hitting this memory location when we execute the previous instruction, which we will be doing as we go around the loop. So I've got that set on the analyzer. We've got F0 E0 set. If we go to the waveform, arm the analyzer, and now I will reset the MIMI, and as you can see we are now successfully triggering, which we weren't doing before, and obviously that's quite a big step forward. The machine still won't boot, so the next thing that we need to do is figure out why. It could be that we've got the formats of the disk wrong, but at least we're fairly close now that the disk can be, or at least appears to be readable by the MIMI. So the next step is to actually read the data. So we're currently here and we know we're reading the data, so all we have to do is scroll through this captured instruction that we now have on the analyzer, and if I start scrolling across, you'll see that we're going from F0 E0, which you can see on the yellow trace on the analyzer, and if we start scrolling across, you'll see that we're going through to the point where, looking at the chip select line, that goes low. The chip select is the floppy drive controller chip. The A1 A0 line, which is the white line just above where it says 3 it's a 2-bit data bus, is showing a value of 3, and that means that the register that's been selected in the floppy drive controller chip is the data register, which is the one we're interested in. And then below that you can see that we have the read enable line going low. That's the read enable for the floppy drive controller, and then below that we have the IORQ line going low, which is the Z80 in-app request line. So when you look at all these together, what's actually happening here is we're trying to read the data register from the floppy drive controller, and it's doing that of course because there is now data in there, and we weren't getting this far before, but we now need to see what data is being read, if any. So if we keep going across, you'll see that there's a bit of noise here, and this is due to this switching on the buses and various things. There's timing skew of course between the various devices. There are buffers sitting between these control lines and the actual devices, and as they all take turns in switching and settle down, you'll see we go through various values. But ignore the interim values. Where it says FF and 3F, ignore those, they're just the data bus settling. Keep going across and we've got a value of 3E, and that's the first data byte that we are reading. Now in theory, as we go through the code, and if you decode this little loop, it just keeps looping round now until the data stops appearing. So this first part is in effect a timeout, and then the next bit is looking for data being ready. It'll keep looping round, and when there is data it will read it, copy it to memory, and when ultimately there is no data and the floppy drive controller busy line is no longer asserted, then the code will exit this loop. So in other words, it should just keep going round this loop, reading data bytes and saving them to memory until there is no more data read from the floppy drive controller. So what should happen now is we should jump back to this address, which is F0D7. So if we keep scrolling across, we can see we do indeed jump back to F0D7. But because in theory we should be reading 512 bytes, what we need to do is change the trigger count so that each time we hit the target address we read a new data byte. Not quite as straightforward as that, as I'll show in a second, but if we start by going back to the trigger, and what we can do is modify the trigger, and we'll change it so instead of one occurrence of this trigger we'll have two. That if all things were simple would give us the second data byte. So we'll reread the disk. We've hit that trigger twice, and if we scroll across you can see we've read 3E. So if I show you the raw data, what I was doing is going around and writing down the data that I was seeing. So if I show you what I captured, you'll see that what I got was 3E, 3E, so I got 6 3Es. I then got 6 61s, followed by 63s, 6 03s again. And that's because the timing for the floppy drive, obviously the floppy drive is quite slow compared to the processor, and it meant that we were going around this loop 6 times for each byte that was read from the floppy drive. So what we actually need to do is increase the count on the trigger by 6 for each byte that we want to read. So if we go back to trigger, and instead of setting it to 2, we'll set it to 7. So that's 1 plus 6. And then go back and re-trigger the MIMI. You'll see that we're now getting a value of 61, which is what I got. And then if we go back to trigger and we increase this by 7 again, that should give us the next data byte. So I'll re-trigger, and we're now getting D3, which is what I got as a third byte. And I went through and did this for the entire sector and ended up with 512 bytes. And the next question was, were those data values correct? So again, I won't show it on camera, but what I did is I looked at the hex data that was in the first sector on the disk, and that exactly matched the data that I captured on the analyzer. So in other words, I can now be fairly sure that the MIMI is successfully reading an entire sector. And so what actually happens is, once it's read all 512 bytes, it will exit this code and it will jump to the target address of F0FD. And so that's what we'll look at in the next video. We'll look at what it's doing once it's read the entire first sector and try to figure out why it's still not booting. Most likely we've got something wrong when we've produced the disks. It's not that uncommon. It's very difficult trying to reproduce old disks because the format can be somewhat variable and ambiguous. Or it might just be that the disks are not actually bootable disks. We don't yet know, but the next thing to do is to see why the MIMI itself is unhappy with the data that it's read from the first sector. So I'll do that in the next video. Any questions, then please leave a comment.